Good morning, beautiful people. We're off to day 3. Exciting primer is coming up on HDR by Pierre, and we hope to continue this conversation. We will have a break at 11:30 to 12:15, and lunch will be 1:15 to 3 p.m. Thank you.
Good morning, brave people who made it this morning. I see some people still coming in, so I'll try and speak slowly at the beginning to let more people come in, and then I'll speak fast at the end. So, the goal of this session is to give you a bit of information on HDR if you are less familiar with it, so that when the sessions happen this afternoon, you are not lost when they use terms like color volume, wide color gamut, and things like that. But also I find I've been giving HDR for SMT for 4 years now, and even when people are familiar with the subject, it's always good to go back to the foundation and basics and get a nice overall view of what it is. So here we go with the short version. So fundamental to understanding HDR and understanding imaging in general, I would say, not just for HDR, is understanding what light actually is. And that's the foundation of color science, HDR, imaging, displays, cameras, and everything else. What's special about light is, first of all, it has a certain variety of wavelengths, which give it its color properties. If we look at light at a very broad term, it's called electromagnetic radiation. The visible portion, the one that we can see, is very limited. It has certain wavelengths that we can see, beyond which you have infrared and ultraviolet. That's our visible light. The difference between light and sound is that sound is also a series of waves. And if I have a high pitch or a low pitch, this is just variations in frequency. But the difference is that sound, it needs a medium to carry it. So we have air in here. If we made a vacuum in here, so by having air, the voice can be carried, but light is different. At night, we can see the stars, we can see galaxies, we can see the light coming from very, very far away, because light has the unique property of carrying its own energy. And theoretical energy particles are called photons. So these are our energy particles. This is why the sun is. Why am I talking about this? Because those two properties, the wave properties and the light intensity properties, are the foundation of every single capture system and display system existing today. Understanding that we can capture light when we filter its wavelength properties, we will capture it through different filters. So either we're going to use prisms to separate light into its constituent wavelengths, or we're going to use chromatic filters to break it down into its constituent wavelengths. That gives us the entirety of colors that we can capture, and at the other end, the entirety of colors that we can display, which is called the color gamut or color space. Or there are different things, but we can call it the same for simplicity's sake. That's one part of it, is perceiving colors. But there's also a certain light intensity that can go from very dark red to very bright red, for example. So the light intensity is measured through photonic emission. So those energy particles, we're going to capture them, we're going to convert them into electrons, and we're going to measure the current, and this is how we determine the dynamic range. So in very strict scientific terms, when we talk about dynamic range, we're talking about light intensity strictly, but when we're talking about HDR, or high dynamic range in displays, we actually combine both. It's a wider color gamut, and it's more light intensity that we're capturing. Okay, so far? So for color space, scientists at the Commission Internationale de l'Éclairage in 1931 sat down together, decided to put some science behind it, basically. And they determined, or they discovered, not that they themselves discovered, but they actually categorized the fact that human vision can see three different types of wavelengths. The cones, or color-sensitive cells that we have in our eye, will react to red wavelengths, green wavelengths, or blue wavelengths. Scientifically, we call them short, medium, and long wavelengths, but they correspond roughly to red, green, and blue. And this is the three colors that we perceive, and our brain will take the combination of red, green, and blue stimuli and create the entirety of colors that we see. So those three dimensions, red, green, and blue, were derived in a mathematical model so that we can flatten it out in a 2D model with coordinates. So that's the small x, small y color representation of what everything that the human eye can perceive. So the boundaries of this kind of rainbow-colored Smurf hat here is the entirety of what the human eye can see. Now into our productions, some camera systems will capture more or less of that. So this is where you have the BT709 color space, the Rec 2020, the ACES. ACES actually captures the entirety of the human visual system, so that's why it's the widest one in use and kind of the ultimate, if you want. So that's for colors. But that just gives us the idea of colors at a certain average light intensity. Colors are going to be reproduced more or less depending on the intensity of it. So when you extrude this model and make it three-dimensional with the other dimension, which is light intensity, that gives you the color volume. So when we talk about color volume, we're talking about the entirety of colors that you can see at all the different light intensities, from the very bright to the very dark. That's the principle of the color volume. So since we're into a HDR session that will focus on dynamic range, I'll talk a little bit more about the dynamic range side of things than the color gamut side of things. So our dynamic range perception is not linear. We have light that, for example, is in front of me. And if I had a camera to capture it here, I will display that light at the very end on a display. It's never going to be a one-to-one. So you have an overall OOTF, which you see on top. It's the opto-optical transfer function. That means the light intensity that I measure in front of the camera and how that corresponds to the light intensity that I measure on the display at the very end. So it's going to be representative of what was in front of the camera, but it's never going to be exactly the same. So it's not a one-to-one, unless we have a display that can do 35,000 nits and represent a bright sunny afternoon in LA, but that's quite a long ways away. So light comes into the camera as photons. The photons will hit the sensor. They will displace electrons, which will create an electric current. We measure that current, which is an analog value at that point, and then we will digitize that value using an analog to digital converter. That will give us code value. So that's the optoelectronic transfer function, taking light measurements into electricity and giving them certain code values, what we call the OETF. At that point, you're still into the scene-referred world. You're still in the camera world. It's not an image that is formatted to be viewed on a display device. It's just a theoretical, mathematical representation of how much electricity was generated on your pixel at that point in time during that exposure. Then after that, we're going to do all of our creative changes. We're going to take that electronic information and we're going to give it a new optical value depending on the display technology that you're going to be using at the other end. That's the electro-optical transfer function, or EOTF. So you go from light, electronic values, and then transfer your code values into a display world so that you can display them at the very end. That's how a modern movie is made. So for those that are into production and shooting, the scene referred is typically what you see in RAW. It's an image that will look all sorts of wrong if you try to display it because the code values are theoretical at that point. They're not made for the display in which you watch it. Add a lookup table, add a transform, use a color managed workflow in post-production, and now you can view your image properly. Like I said, we're in a digital world, so we have to take those analog current measurement and give them a discrete value. That is a process called quantizing, basically giving it a quantity, a defined quantity. You can think of it as a histogram. You have different code values, and each code values has a certain range. So from this many millivolts to this many millivolts is this code value. So you have to give it boundaries because in a digital world, we work with ones and zeros. We don't have infinitesimal values. So you have to give it a certain code value. The more bit depth that you would have, so the more bits you have to express that curve, the less it will look like a histogram and the more it will look like an actual curve, the more faithful your information will be to what the camera actually saw. So increased bit depth, more faithful representation of the source, gives you more room in post-production to do fantastic things with your high dynamic range images. So as a guideline, the typical bit depths that we have in production, HD TV was 8 bit, so 2 to the power of 8 because a bit is a 1 or a 0. So it's a base 2 system. So 2 to the power of 8, 256 levels. So it's not a lot of levels, but it was sufficient with the color space and the dynamic range of 709 to be able to represent an image without excessive artifacts, what we call bending, because you don't have enough code values. Definitely not enough for high dynamic range. If you try to produce high dynamic range images in 8-bit, you're going to have a lot of bending because your color volume is a lot bigger. So in a display world, we're going to use 10 bits. So 2 to the power of 10, so 1,024 levels. That's enough to represent a high dynamic range image on a display. You're going to capture at a higher bit depth than that because you want to have some freedom in post-production to play with the levels, bring the light down without artifacts, push some things up. But for the display side of things, 10-bit is enough for high dynamic range. If you want to go into higher dynamic range for a capture, we're going to go in 12-bit if you use a logarithmic space. So like I said, human perception not being linear, you can have more code values at the beginning, less code values at the end. So that's a logarithmic function. So by using 12-bit logarithmic, we're able to capture a lot of dynamic range. This is, for example, every RAW is 12-bit, and a lot of other cameras are. And then if you want to have an infinitesimal, almost infinitesimal amount of code values, you're going to go to 16-bit. At 16-bit, with 6,500, 536 levels, you have so many that you go beyond what the human eye can actually perceive as changes in luminance. So you don't have to have the logarithmic encoding. You can keep it linear. The reason why you keep it linear, it's easier to merge images that are captured with images that are generated by the computer because the computer is a linear system. So that's why systems like ACES, Sony RAW, Red RAW, and a lot of other companies will use 16-bit scene linear. But these are hefty files. It generates a lot of data because you have many, many levels to encode. So on a high-budget movie, you will do this. Maybe you will use 12-bit on something where you don't have terabytes and terabytes of data processing capability. The major formats, there are other formats than this, but these are the ones that are the most widely used right now. And since I have limited time, I cannot spend a day covering everything that exists. So we have 3 major formats: HDR10 and its collateral HDR10 Plus, Dolby Vision, and hybrid log gamma, the 3 major formats that are used. So I'm not I do not want to get into a political argument about which one is best and why we have multiple competing formats, but I'll give you my impression on why the situation is the way it is right now and why we have these multiple formats and who prefers which format for which reason. So it's a bit editorial, hopefully not controversial. HDR10 quantizes at 10-bit. It's a display format, really. So it quantizes at 10-bit, and it uses the PQ transfer function. The PQ transfer function was designed, and we'll talk about it a little bit later, it was designed with human perception in mind. So more code value allocation in the darks, less in the highlights. Covers up to 10,000 nits on the display. It has certain metadata with it. If you are working in streaming or non-Blu-ray disc, will typically give you the mastering characteristics, so you know if the content was mastered on a 1,000, 4,000, 10,000 nit monitor, which would be great to have a 10,000 nit monitor, but another story. So it will give you the coordinates of the color primaries, the white point, and the display's characteristic. And the reason why this metadata is provided is because the display you have at home may not represent the entirety of what was mastered with your $35,000 post-production monitor. So the TV has some information, if that mode is activated by the manufacturer, to actually tone map the image so that it gives you the relatively the same creative intent as what was seen in the mastering room in your home. And then for Blu-ray, they give additional information, basically what we call max fall and max CLL, which is basically what is the brightest on average frame in your entire content and what is the brightest pixel, which is of limited value, I would say, because you may have an explosion and have one very bright pixel in the entire movie. It doesn't tell you about the way the whole movie is made, but that is what we call static metadata. It's one set of metadata that accompanies the entire file, whether it is a 1 minute or a 1 hour piece of content. To provide more accurate and more tone mapping options, there are new formats like HDR10 Plus that will provide you with dynamic metadata. So basically every frame comes with its own set of metadata so that the television can tone map more accurately based on what each scene actually is. Dolby Vision is kind of like HDR10 Plus in the sense that it has dynamic metadata. It uses also the PQ or ST2084 transfer function. In theatrical, it is 12-bit. In the home, it is 10-bit. What Dolby does on top of it is they manage the ecosystem. So from your mastering to the display at home, if a display has Dolby Vision, it means that its profile and the way it's going to tone map the source image is approved by Dolby to be faithful and preserving the creative intent of what was mastered in the original room. So it's a more closed ecosystem since it's approved from end to end. That's Dolby Vision. So both used ST2084 as their transfer function. So just a couple of words on the transfer function itself. Was developed by Dolby. And basically the reason, like we said before, we have more code values used for darker areas than we have for highlights, which corresponds to the way we actually see the world, like we said. So it allows them to compress the whole dynamic range very faithfully and give them something from 0 to 10,000 nit range without apparent visible bending in 12-bit and very limited bending in 10-bit. So it's a very powerful transfer function. Where it's different from other transfer function, we'll talk about hybrid log gamma right after, is in the fact that it's an absolute transfer function. It's linked to the displays, not the display's performance, but to actual light values. There's a certain code value for 1,000 nit, And whether your display can display a maximum of 700, 1000, or 4000, that code value equals 1000 nits. So it prescribes certain luminance values for the display to show you. And if the display does not go up to that point, then the display will have some sort of a knee where it will gradually blend your highlights towards white so that you don't perceive like a very aggressive cutoff. But it will not go with the percentage of your display. It's not going to map relatively to your display's capability. It's an absolute system, where HLG is different. HLG, or hybrid log gamma, pioneered by BBC in the UK and NHK in Japan. They use a kind of a hybrid system. Well, it's in the name. Wow. I'm not a genius here. So basically what they thought was that the gamma function that is used in 709, it kind of effectively gives you more code value in the low areas. So why not use that part of the original transfer function for high def? But in the highlights, it clips very quickly. So why not extend it with a logarithmic function? So it's a combination of the gamma the gamma transfer function from HD and then logarithmic for the highlights. Allows them to capture up to 12 times more highlights than with high def television. The difference, the main difference between HLG and PQ is that HLG is relative. It will give you a code value that will say, give me 70% of the total TV power. It will not tell you, give me that many nits. So if you add 100% and your TV can do 1000 nits, your highlight is going to be at 1000 nits. If the TV can do 700, your highlight is going to be at 700 nits. So it's relative to what the TV is able to reproduce. So it's different in that sense. It's like what HD used to do, basically. One of the reasons why it's popular is because you don't need to carry any metadata. There's no tone mapping that is applied to it at the display side. So basically, if you have infrastructure that can carry a 10-bit signal, it doesn't know if it's high def or if it's HDR. Or, I say high def, I should say 709 because you can have UHD with 709. It doesn't know what is being carried. It will just carry it. So it allows you, if you have, for example, a 10-bit switcher, you can do an HDR show. You don't need to have a special equipment that carries static or dynamic metadata. So that's why it's very popular for live applications, because you don't have to generate any metadata. And so we have typically, it's decaying a bit, but it's still relatively faithful to what's happening in the world, because with COVID, things have kind of slowed down. We have, I should say, two camps, if you want, in HDR. One camp that is content that is created, post-produced, catered to, and in that case, you want to protect the creative intent all the way to your final viewer. These are more in the camp of PQ transfer functions, so either HDR10, HDR10 Plus, or Dolby Vision, or a combination of those. That gives them certain assurance that the end result will be like what they intended when they were mastering it. So most of the OTT channels that have pre-recorded content will use it, as you can see here. When we look at live, it's a different story. The concern for live is to have backwards compatibility, be able to transmit it, get a good experience sent to many people without having to change and overhaul your entire live production ecosystem. So it tends to be geared a lot towards HLG for live applications. So as you can see, two different markets, two different kinds of needs, two different types of transfer functions and approaches. And that's all the time I wanted to take, because I want to leave time for questions. But this morning session is intended to give you a little bit of background so that when you hear those terms this afternoon at 3 o'clock, and I hope you will all be there, you can make more sense of what is being discussed. So the floor is open if you have any questions. Oh, over there. The microphone is coming.
Thank you very much. Could you please briefly touch base on SL HDR1?
Yes. So SL-HDR1 is a format that is being used, developed by Technicolor back in the days when I was actually working at Technicolor. SL-HDR1 is not a different format per se because it uses the PQ transfer function. It doesn't use its own transfer function. But what it does is it provides additional information to your SDR broadcast so that you can actually create HDR out of it. And taking that additional information, it will build the highlighted formation and give you your PQ image in the end. The reason why some people are using it is because it's backwards compatible with SDR. So if you have a content that is a TV that is not HDR enabled, it will still see it and decode it as SDR. But if you have an HDR enabled TV, it will take that supplemental information and make it HDR. But at its basis, it is PQ based. No other questions?
Can you discuss the consumer electronics side of their ability to automatically select the appropriate HDR format in the consumer equipment rather than have it a menu selectable item?
Absolutely. So the way HDMI has been developed from beyond HDMI 1.4 is that the information about the transfer function is actually included into your HDMI signal, so it carries with your from your player or your set-top box or your computer or your Amazon stick or whatever will send that information directly to the TV, so it knows which transfer function to use and it will switch automatically. That is great for the consumers because you don't have to go and select a menu and use the wrong transfer function and everything looks weird. It's a bit of a challenge on the professional side because if you want to use for confidence, for example, in post-production, I have a reference monitor, but I also have a consumer display because I want to see what it looks like. I cannot manually go and tell that display to use this transfer function. So I need to add an extra box. So props to Aja, who I use their Hi5 Plus box. Basically, take my feed from the computer, get it in, inject the metadata to tell it which transfer function I want to use, and then HDMI to the TV so that the TV is in the proper format. So I guess that answers the question. For broadcast is the same. It needs to be flagged when it's transmitted so that your set-top box can recognize the signal and decode it. That creates some sort of challenges when you want to do wide broadcasts of HDR. If I'm in a consumer home, for example, that has an HDR-capable TV and a non-HDR-capable set-top box, it will not work. I have an HDR-capable set-top box, an HDR-capable TV, but I've installed an amplifier in between for my audio. It's an HDMI 1.4 amplifier. It will strip the metadata. You will lose it, and you will not be able to see it. So there are significant challenges to standardize viewing experience on cable, which is why a lot of the HDR experiences right now will be consumed directly by smart devices inside the TV so that it can flip the TV into proper mode through an OTT transmission, avoiding all of this nightmare of I'm calling consumer service because my TV doesn't work in HDR even though it's an HDR TV.
Can you talk a bit about how the metadata gets stored?
About how metadata gets
stored in the video signal? How does the metadata get stored?
Sorted? Stored. In the case of max CLL and max fall, it's part of the Blu-ray disc information. So it's transmitted. I don't remember exactly the method, but it's part of your header that has that information. The vast majority of display devices will just strictly ignore it and not work with it. Higher end displays will take it into consideration, but it's a small amount. As for HDR10 Plus, that's a proprietary thing with Samsung and their devices where they have this dynamic metadata exchange, and with Dolby, it's their own system as well for the dynamic metadata exchange as part of the stream. And I think it's the last, or we're going to run out of time, right?
Max fall, max CLL. We know the limitations with those two measurements. Can you comment on the fact that, a lot of production companies are requiring QC using max fall and max CLL, and you continue to hear complaints from people who are doing QC that this doesn't really make sense. Do you have any thoughts on that?
Yeah, you need to compile them if you're delivering for a Blu-ray, for example. You need to compile max fall and max CLL and provide those values. As QC instruments, they make sense if you're plotting over a certain period of time. But if you take, for example, max content light level, it just tells you what is the brightest pixel on the screen. If I look at this room in here, 95% is at a very low level. If I was capturing with a camera and limited highlights blowing on those, I would be around 30% probably light intensity. But my max light level will be at 100% because of those highlights, which are not really part of my story here because I want to capture my audience. So it has very limited value, in my view, as a quality control tool. You provide the numbers because it's asked of you, but as a control quality tool, I prefer to use distribution of light with my waveform, or as I talked about yesterday in my wide color volume presentation, we give ourselves certain thresholds and boundaries to see if a scene is generally over or underexposed, if it's slipping, if it's in dark noise, or if its general distribution is too high or too low. And I find these to be a lot more efficient for quality control than using just the maximum light level or the maximum average frame light level. Thank you very much. I think that's all the time we have. And I hope to see you all this afternoon. Please be there for our excellent presentations on the HDR.